So I'm Jonathan Wright, and this is my lab report on magnetic braking with Faraday's law. So for the intro, the key results, the goal of this lab is to collect data with a magnet that falls through a conductive tube, which will illustrate that there's an induced current produced by the changing magnetic flux, which involves Faraday's law, which we'll get into in a bit. And just to give you a peek into the key results of the lab, the time for this magnet falling down the tube is 1.04 seconds from the predictions, and the actual result was 1.25 seconds. So the key concepts are Faraday's law, Lenz's law, and magnetic flux. I'll start with magnetic flux. Magnetic flux is just the integral of magnetic field across a surface. So for this case, we'll say that this rod has n loops. Then you calculate the flux across the surface for a particular loop, like the magnetic field for the loop. Then you integrate it from the surface of that loop, and then you multiply by the number of loops, and that'll get you the total magnetic flux. Faraday's law says that the derivative of that magnetic flux is going to be equal to the electromotive force, like the induced current produced by this material, by the rod multiplied by its resistance, which is EMF, of course. And Lenz's law tells you the direction of that, which essentially nature abhors the change in flux, same thing as we learned before with electric flux. And so it's going to counteract that change in magnetic flux, basically. So the experiment, the experimental data and the procedure. So the procedure is a pretty simple one. Give you an illustration there on the left. You just drop a magnet through a rod, and I could get into it, but I won't. But the direction of the magnet doesn't really matter. Like it actually, no, it's not, doesn't really, it just doesn't matter. And I gave you the measurements of the magnet there on magnet and the rod on the middle of the screen. For assumptions, the key assumption is that we ignore air resistance, as that it's going to be pretty pointless because it's not going to be moving that fast. And on the right, I showed you the time, so we're measuring the time that it takes a magnet to fall through this rod fully, starting, when it hits the top of the rod, and then measuring when it falls out. And yeah, the average was 1.236 seconds. So for the VPython model that we're supposed to create, there's a whole bunch of stuff here. However, I'm going to focus on what's in the bottom right, step 3 for calculating the magnetic flux. So what we're doing here is we're making a function to calculate to return the magnetic flux for an individual ring, and then we sub this function in using some sort of loop later on. We put that function for each individual ring that's in the rod. And so what we're doing in the function for calculating the deflux dt is that we're just taking the magnetic field, multiplying it by the area, and the area is just going to be pi r squared. Yeah, that's really all there is to it. Oh, right, then you have to take the derivative of it, which involves velocity as the position is changing with respect to time. And the dx dt is going to be, speed. That's the key thing there. And so for the results of this model, there are some fancy colors and graphic stuff also there. You see on the left, that's at the very end where the rods, or where the magnet's almost at the bottom. The colors illustrate the different magnetic, or the different, magnetic fields that are felt on the magnet. No, it would be electric fields that are felt on the magnet. The different currents produced. You see the velocity versus time function, and yeah, the key thing is here is that the result is 1.042 seconds, which is fairly close to the experimental result. However, it's undershooting what we got from the experiment. So for the two discussion questions, first of all, for the first question here, the falling magnet would fall much slower if the resistivity were reduced to 0, as IR equals EMF. And so if your resistivity, or if your resistance is lower, your current's going to be higher, and that current's going to increase the force felt by your falling magnet. And secondly, if holes or slots are cut into the tube, this is pretty simple. You're basically going to get less rings, as there's less, there's quite literally less rings here because you have holes in those rings. And so yeah, it'll make the magnet fall faster and less current.